Doing da 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 da. I did it, I got it.
Is he the only one? Has anyone in here done it?
No.
Jose,
So-
get it done.
Now, in my defense though, guys, if you get this sometime this year, you will beat my time record because I've had this thing for like 3 years. This is the first day I got it.
Give it to Hayes.
I've done like 20.
No, I put in more time to it, but this is the first day I've actually
If
sat
I
down
do
and got
it-
it. But
if
so,
I
yes.
do it,
Jose's on
What was
18.
your reaction?
I literally went, ooh, like that.
Mr. Dow, I
something
think
along those lines.
the winner, our class is exempt from the exam. You?
No.
Seniors are exempted.
Okay.
No, where's
So, what we're going to talk about right now, everybody, okay, is reminder to you all, we have a test on Thursday, okay? This is basically a list of what to expect for the test on Thursday, okay? No, I said we're going to have the one. We're not having a test the last week. That's what I said before.
Oh,
It's this Thursday, yes. No, not next Thursday. I'm not crazy. I'm not giving you a test next Thursday.
You're
You
so
have an
kind.
AP question due that day, but no, we're not having a test that day. In fact, there's a good chance we'll probably just end up watching The Grinch Stole Christmas. Okay?
Actually?
The original Chuck Jones cartoon version of it.
Wait, are you serious?
I'm not joking with you on that one. I did that last year. I'll probably do it this year. Okay.
How many days is that gonna happen?
Jose.
Once.
Oh, well, isn't
Come
it?
on,
It's longer than 45 days, or 45 minutes.
That's just
I'm not
not.
talking about the Jim Carrey movie version. I'm talking about the.
That's more than 45 minutes?
Like half an hour.
Yeah,
If that.
Really?
Like the one with "You're a me."
Yeah, I know.
Yeah, the Chuck Jones version. With
Cindy Lou
Rose Color.
They both have Cindy Lou Who.
Anyway,
Cindy Lou Who
Okay.
is like a character, just like the Grinch is a character.
all right. So, this is kind of a recap of everything we've been talking about, okay? And we're going to go through and cover a few little things today to kind of finish this out, okay? Tomorrow and on Wednesday. If you have questions about anything test specific, ask me them on Wednesday. I'm not doing a review session or anything like that. If you have questions about things you missed because you weren't here on Saturday or something like that, there are videos and notes posted online. Watch them. Watch the videos, read the notes, okay? That's why I do this. That's why I'm filming myself right now, okay? But basically, yeah, you guys keep talking, there definitely won't be a Grinch movie. Calculate antiderivative or indefinite integral. That's the big thing we've done first. Do the rectangular method of finding area, that is taking a Riemann sum. Know how to do that. Know how to calculate a definite integral, and I gave you what definite integral is. Okay. And lastly, this is stuff we talked about yesterday. Common to definite integral properties. Those are the those will definitely pop up. You want to know how to do those because they help you out. What we're going to look at today is a few other things that are going to be on the test, or rather, they fall in each of these categories here, but there are ways to do them for things. Like, for example, using your calculator to do a definite integral. Calculators can do definite integrals just fine. We're going to take a look at that. We're also going to look at another relationship you'll see between, if you remember, in the fall, we talked about how big type of problem was particle position. We have position. The derivative of position is velocity. The derivative of velocity is acceleration. Well, guess what? If you flip that around, the antiderivative of acceleration is velocity, and the antiderivative of velocity is position. Okay? And so we're going to take a look at that as well. Plus, we'll also see today how you can find, if given a point, how you can solve for C. Okay? Which is very important, which is something you'll want to be able to do. Okay? Does everyone who's taking notes have this down right now?
No.
Okay. Give you guys a
How do you
second.
spell that? R.
Riemann. R-I-E-M-A-N-N.
This is everything that's going to be on the test.
Yes. Okay.
Oh, you're a genius.
I don't care if you guys use phones or iPads to take photos.
Mr. Dowell.
This is the 21st century. I was about to say 20th century. That dates me.
I'm gonna finish that.
Did you go see the Bluegrass guys on Saturday?
I wanted to, but Robbie is sick, and was feeling very fussy that evening, so we took him off.
What kind of sickness does he have?
He's got like a really bad cold apparently, and he didn't seem all that sick, but like occasionally he would just have these like he'd just cough a lot, and so my wife eventually was just like, no, we should probably take him to the doctor, especially because he's been kind of sleeping a lot more than usual, and it's a good thing she did because apparently like yeah, he's got a cold that's bad enough where he needs to have like a nebulizer thing. It's like a nebulizer is the thing it like yeah, it like atomizes the medicine and you breathe it in. So it's like it looks like it looks like fog or smoke or
Looks like a
hookah pipe or something. Okay. Medicine. He actually needs one, so that's kind of crazy.
What's a hookah?
Look it up.
That's what your mom and dad puff around
All right.
in the garage and stuff like that.
Okay, so let's start off first. Our first example we're going to start off with is how to use a calculator to do a definite integral. Okay, so here's a definite integral written up here. Okay, so we're going to look at using a calculator. Okay, so here we have a definite integral here example. Okay, the definite integral from 2 to 5, the square root of x squared plus 9. Now, with the rules of integration that we know so far, can I do this?
Yes. No.
No. I can't rewrite this into something that's a standard polynomial. I can't break it apart because of that stupid square root. Okay, as it's currently written, and there's no other tricks that I know of so far that can currently handle this. This is not something you all can do right now, okay? It's actually also not something you would do anyway. This would actually be a very difficult and nasty antiderivative to take by hand, okay? I know, it seems so simple, right? This one would be ugly to do by hand. But we don't have to do it by hand. We can do it with a calculator. And in fact, the calculator is exactly how we'll handle this guy, okay? If you bring up your TI calculator, wake up, okay?
Never mind, yes I did.
Okay?
Thanks.
Okay, so there are multiple ways, there are 2 ways you could possibly do it on your calculator, okay? Some people have fancy enough calculators where they can hit the math button, okay? And scroll it on down, there's an option that will read FN interval, INT like that. That stands for integral, basically to do the integral, okay? Some people's calculators, if you bring this thing up, will actually write basically out and ask you what are the limits, what's the function, etc. My calculator does it. It's asking me to do this some other way, some way that I don't know how to program it to do. So this would not be a good way for me to try to do it, okay? But there's another way I can do it. I can the graphing utility of a calculator, everybody. Okay, just hold off. Don't throw it.
I was just gonna hand it off to him.
Okay.
Pass it down.
Pass it down. Thank you.
Mr. Dowell, I'm
Okay.
an athlete.
All right. The other way we could do things here is we can actually graph them. Okay, using the graphing utility in the calculator, and in the calculator's tools, in the calc menu, there's actually, okay, guys, zip it, okay? There's actually a function in which you can calculate an integral. So I would just graph this as written, okay? Okay. Whoops.
Hello.
Go ahead and graph that. Okay, and you see the graph would look something like this curve right here.
Why did you do trace instead of graph?
It doesn't matter. I just always hit the trace button. Trace just redraws the graph every time. Okay. All right. So there's the graph of this thing. This is what the thing looks like. If I want to calculate from 2 to 5, if I go up into the calc menu, okay, I have these options. 6 and 7 are for calculus. 6 is to calculate the derivative at a point, and 7 is to calculate the definite integral over a zone. So if I choose 7 down here, it's going to say, what's my lower limit? That's 2. Okay. What's my upper limit? That's 5. enter that in. Calculator does its thing, and it gives me that this definite integral here is equal to 13.936 in size. It even highlights the zone in which you're doing it, as you can see up there. Okay, making this thing excellent to use to calculate these things out. Okay, any questions on how that works? Yeah.
I'm sure the definite integral is the difference between the top.
The antiderivative of the big number minus the antiderivative of the bottom number. Okay? The thing is, we can't do the antiderivative of this function easily. The calculator can do it just fine, so we use the calculator. Okay? Yes?
So you plug in the graph, just the x squared plus 9
Square root of x squared plus 9, yeah. So when I graphed it, I just graphed the function. Okay? And to do the integral, I hit the second calc and just type in the limits of integration. That gives me.
How did it know to do the derivative?
It just knows. It knows how to do the antiderivative. Actually, it's doing a Riemann sum with lots and lots and lots and lots of rectangles.
Yeah, but if it's grabbing that, don't you need the derivative of that? It just automatically does it?
Well, antiderivative is what we need.
Antiderivative, that's what it is.
Yes. And no, again, because remember, you could do a Riemann sum, which is you're taking a lot of rectangles of the same width and adding them all together. The calculator is able to do lots of rectangles very quickly. So it's doing really ridiculously thin rectangles and adding a ton of them together and giving us an approximation of the area that's close enough for our purposes.
That shaded zone is your answer.
Yes.
How did you get to the points again to do that?
Okay, again, they're given to me right here in the integral, 2 to 5, to put them in the calculator. I hit second, trace, which brings up the calc menu.
Trace?
Yes. It's the one that says blue and calc.
Yeah, no, I know. I was just saying.
Second trace.
7.
Option 7. Okay. It will say lower limit. That's 2. You just hit 2, enter.
5. Alright.
And then 5, enter. And
So-
the calculator does its thing. It gives you the answer.
What about on the easier ones? Would you say that we can use the calculator on that?
It depends on the question. Just like the AP, there'll be some times where you're saying, yeah, you can use a calculator, in which case, if you want to use the calculator, use the calculator. There are times where it's told you can't use the calculator, and that's why we know how to do things by hand.
It's the f of b, big F of b minus big F
In
of
fact, let me show you an example where the calculator may not necessarily help you out very much. Okay? This was calculating out a definite integral. Okay? Akin to calculating out a definite integral is finding the area bound underneath the curve in the x-axis. Okay? One thing I've been harping on, and this is something I said the other day, is that the area between the curve and the x-axis is modeled using the definite integral, but they're not the same thing. Okay? Definite integrals, okay, can be used to represent the area, but they're not the area. One reason for that is because a definite integral can be negative. An example of that would be this one right here. I did the definite integral from -2 to 1 of x cubed dx, okay? That antiderivative is x to the 4th over 4, which I evaluate from -2 to 1, plugged in my numbers there, worked it all out, and got an answer of -3.75. Okay? That's why, yes, when you split them into the absolute value. But basically, I want to point something out here. For a definite integral, this is a perfectly fine answer. If I'm just asking what's the definite integral, -3.75 is the answer. But if I'm asking instead, what's the area bound by the curve in the x-axis, this answer does not work because it's negative. Okay? Area cannot be negative. Area has to be a positive number. In fact, what's going on here is in my little graph right here, okay, this whole part of the graph is counted as negative. So the integral says this is basically the integral calls that negative area and treats it as such. Okay? Now, for calculating a definite integral, that's fine. We don't care about that. It could be negative all day long. No problem there. Okay? But if I'm looking for the actual area, the actual physical space, it can't be negative. And so what you have to do is you have to graph it, graph it or find zeros or whatever. Look to see where the thing crosses the x-axis. This one was easy enough. It crossed the x-axis at 0. Okay? And then break my integral into 2 using that number there. And so that's when I use the absolute values. Okay? So I rewrote this thing for the area this thing is equal to the absolute value of the integral from -2 to 0, plus the integral from 0 to 1. And when I do the math there and add it all up, I get an answer of positive 4.25. Okay? So, notice that's a lot different. That's a pretty big difference there.
How come you didn't need the absolute? You just don't because there's no negatives on that second one?
Oh yeah, there's no need for it. I mean, technically speaking, if you're being like really meticulous, you put the absolute values around it, but you don't need it because again, it's always positive. From 0 to 1, it's going to be positive. We can see that from the graph.
And
Okay.
I may have missed this. But what is that? Is that word calculator work under the first step?
Oh, right up here?
No. You sort of started yeah, under that. Yeah. What
No, I did that one by hand again.
Was that on Saturday? I wasn't here.
Uh,
I can go.
it's not really. It's just evaluating an antiderivative. So if you've got it's just f of b minus f of a for this first one. Because we know what the antiderivative is of this function right here because we did it above here. It's that right there.
Okay.
So I'm just evaluating that. So when you're doing a definite integral, it's the antiderivative evaluated at the top number minus the bottom number. So here, top number minus bottom number plus top number minus bottom number. And because we're doing absolute values, instead of being -4, it comes out to be +4.
And why are we using 0 in there?
We're using 0 because that's where the graph went from negative to positive. Okay? Notice how the stuff was negative down here? 0 is where it crossed. You basically do it for 0. So if I chose a different graph, for example, if I did like f of x equals x squared, okay? So if I did the integral, from 0 to 4 of x squared dx, and I wanted the area bound by this guy, my break would happen at 2, because 2 is the 0, or not 2, I'm sorry, let's make this actually 2. There we go. Okay, 2 is the solution to this thing, right? It's where it crosses the x-axis. So I break this apart into, from 0 to 2 of x squared minus 4 tx plus 2. Okay? And that would give me the answer. So I just chose the zeros of it. Okay? By the way, when you break apart an integral this way, you can break it up into as many integrals as you need. Okay? As long as the numbers I break it up are between the limits of integration. Okay? So this example right here, we're doing a definite integral from 3 to 7 of f of x. I can rewrite that as the definite integral from 3 to 4 of f of x, plus the definite integral from 4 to 6 of f of x, plus the definite integral from 6 to 7 of f of x. Okay?
So you can do 1 to 7?
I could, not 1 to 7.
Sure, yeah.
Because 1 lies outside that. But I could do like 3 to 3.1. 3.1 to 3.5. Yeah, it doesn't matter. I can do as many as I want to. Now, obviously, some of that would be silly and stupid because you're just creating yourself more work to do. But if necessary, it can be done. Okay? Yeah?
When would you have to use more than 2?
Maybe I had like a really big like area I'm trying to do. So maybe it's like something like I could have like x to the 4th, I don't know, plus something, plus something, plus something. And it could come down like so, come up, come down again, and then go back up, making like a big W shape. And maybe I'm asking for the area bound from that point right there to that point right there. That would be a lot of different integrals, right? There'd be this first one here to whatever this 0 is, then from that 0 to that 0, all that area, from this 0 to this 0, all this area, from this 0 to this 0, all that area, and then finally from this 0 to the end, that little snippet of area. Okay, so that would be 1, 2, 3, 4, 5 integrals that you can break it apart into. Don't worry, I'm not going to give you anything like that on the test on Thursday. You're probably not going to see anything like that on the AP, because it's just kind of silly. But it's just, you still got to know how it works, okay? And likely too, if you ever actually had to do something like that, a calculator would be handy. Okay, you'd be allowed to use it for something like that. Okay? Does everyone see how that works though? Does everyone get the difference between area and definite integrals? Okay? You have to be very careful. You'll know which one you're supposed to be doing because if a problem wants you to calculate the area, they will tell you find the area. They will use the word area. The word area does not appear. You can safely assume it's just a regular definite integral and just go with it. Okay? Okay? All right. Kind of moving on to the next step. Again, want to illustrate the whole relationship between position, velocity, and acceleration. If you remember, the derivative of position is velocity, and the derivative of velocity is acceleration. Likewise, the integral of acceleration is velocity, and the integral of velocity is position. Okay? So keep those in mind. Now, I wrote it with the plus c's up there. Just to illustrate, there is going to be that plus c, remember. When you're actually finding this out, this thing's just straight up equal to v of t. If you didn't write the plus c, that'd be fine. If you're actually, because this is just representative of what they are, okay? The thing is, you can actually figure out what plus c is supposed to be if you're given some extra information about the function. And that's what I did in this example right here, okay? We did an example earlier of working this out, and I said the acceleration of a particle is given by a of t equals 6t to the minus 4. What is the velocity's equation when at t equals 0, the velocity is negative 11? Okay? So the first thing I'm going to do...
Can you scroll back to the...
Yeah, 1 second. Okay. What I did here is I took the antiderivative of acceleration. Okay, so the antiderivative of 6t minus 4 is 3t squared minus 4t plus c. Okay? And that's going to be equal to v of t. Okay? Now, I'm given a point. I'm told that when t is 2, the velocity is negative 11. So, I can set this thing up here. I can replace t with 2 and make v of t negative 11 and then solve for c that way. Which is what I did right here to get c is actually negative 15. So, that meant my velocity for this system, okay, I could actually solve for the c in this and get the flow-out equation for velocity. 3t squared minus 4t minus 15. Now, if I was asking for a nice reason why that's good, is if I was asking for position as well. Okay? I now have the c I need to actually help me find position. Okay? And then I'd have a new c that I'd have to solve, and I'd be given stuff about the position as well. So you're able to go through and figure this all out based off of this. But this is the relationship up here that's preserved. Okay, so hey, scroll back up for you. Okay, you can put down the puzzle ball. Okay.
Gotta learn, dude.
I am.
This Dowell.
Got it.
Okay.
This Dowell.
Just saying my name.
Same day.
All right. Okay. All right. Any questions? Okay. Wait for. I see pencils still scratching. They're not making doodles. They're taking notes.
So you won't give us one like the 5 on the board?
No. No. Maybe if I'm like trying to be cute or something, or if I'm like trying to make you guys do like, I don't know, if I was feeling, I would not have you in all seriousness do something like that. Okay. I might throw it along as like, maybe if I gave you a quiz and put a bonus question in the quiz, that could be the bonus question. Just something absolutely difficult and ridiculous. Okay.
So why is that so hard though? Why don't you
Well, it's not so hard. It's
take
just
it
there's
3
a lot of
times?
different integrals involved.
But you just take the integral 3 times with it.
Well, no, he's talking about the graph beneath, which would have to be split into 5 by whatever the equation is. And so it's just a lot of work to do by hand.
You know, still now.
Okay.
You show that one?
Yeah.
I'll tell you, this phone thing is a lot nicer. I dig it.
Especially useful for
This is
especially
how
for
they're
useful for Graham because he's always on his phone.
Okay, that's a myth. So we just take the old antideriv
Uh-huh. The old antiderivative.
And then plug in 2.
And figure it out. So, all right.
Elementary, my dear Dowell.
Okay. Is everyone good on how Riemann sums work? Do we need to explain how that works? We spent a lot of time on that.
Really like the top.
Yeah. So basically, here's an example of a Riemann sum problem. Okay. Calculate the area bound by the x-axis from 1 to 9 using 4 rectangles bounded above. So note, the problem itself does not say Riemann sum. In fact, a lot of times when you do these problems, they don't say Riemann sum or take a Riemann sum. They instead just say approximate the area or calculate the area using rectangles, bound, etc., etc., etc. Now, people keep complaining, well, if I know how to do the antiderivative of the function, why do I need to use this method? And again, I'm choosing functions that are easy to do that we can actually work out quickly as for examples. Typically, you would use this method, typically this is reserved for ones that we're not given the function. So no function, we just have to we're given a chart with information on it, and we have to use that to do the Riemann sum. We had an AP question, in fact, due the last day before Christmas break, that you do exactly that, okay? The other thing you sometimes have happen with these things is you have a function who you can't do the antiderivative of. So for example, if I had given you this guy and did a Riemann sum of this one, I can't do the antiderivative of that one by hand. And the calculator, and I could use the calculator, but perhaps we just want the Riemann sum instead. Well, that's why we learned that. But all the Riemann sum is you're gonna partition the thing out into rectangles of equal size, or equal width, excuse me, not equal size, equal width, okay?
It doesn't matter how you partition.
Well, it does, because it'll tell you how many rectangles you want. So in this case, we said 4. So, by 4 rectangles bounded above. So, basically, I take the distance between 1 and 9, divide it by 4, so it's 8 divided by 4. So each of the rectangles for this Riemann sum has a width of 2. Okay? Then I just map out, where would that be? Well, the first one would be from 1 to 3. Second one would be from 3 to 5. Next one from 5 to 7. The last one from 7 to 9. Then it's just a matter of, am I going to base them on the upper Riemann sum or the lower one? Or some other point in between? If I do upper, I'm choosing the big endpoint. Okay? So my first partition here, because I was doing upper, from 1 to 3, I chose 3 for the height. So the equation for the area of this rectangle is the change in the distance, which is 2, times f of 3, because that would be the height. Okay? That's one rectangle. Okay? And you do that for each of the rectangles going up. Okay? If I did lower, I'd choose the smaller number, so it'd be 2 times f of 1. Okay? And then, so on and so forth for each rectangle. Okay?
Wait, the change of the distance, which is 2.
Yep.
What is the height?
Times the height, which you figured out by doing f of one of the endpoints. Okay?
Okay.
And you do the same, so if I'm doing upper, I choose the bigger of the endpoints. So this one becomes 2f times f of 3. The next rectangle would be 2 times f of 5. The next one would be 2 times f of 7. The last one would be 2 times f of 9. Okay? That's for the upper one. Yeah?
So, why would you take the area from 7 to 9 if it's not under the arc? Is that
Oh, it is, because the drawing just stopped there. Yeah.
And how do you know when to do upper or lower?
It'll say so in the problem. Okay? And by the way, it could say upper, it could say lower, it could say by the midpoint. Okay?
How would you do by the...
Would that be 2?
It'd just be 2. So it'd be 2 times f of 2, plus 2 times f of 4, plus 2 times f of 6.
Alright.
Okay.
And then-
Heck, it could even say do it for the 2/3 part, or the 1/3 part.
It would be
Okay.
lower, it would be 2 times take the less one, so f of 1.
Yep. Okay. You could do a Riemann sum with the point anywhere on the partition, as long as you're doing the same general point each time. So I could say, do it with a Riemann sum with the equal widths using the quarter point of each partition, which would be dumb and stupid, and no one would actually ever do it this way. But you could if you wanted to. It'd be one type of Riemann sum.
Hayes, that's for you.
Okay. By the way, excuse me. When you're doing a proper Riemann sum, the widths of the rectangles are always the same. Okay? Occasionally, like I did see it on an AP question last year, they actually had each rectangle have a different width. Okay? And if that's the case, it really stops being a Riemann sum problem and turns into just a regular geometry problem. Okay, and they did that like on last year's AP. They had endpoints at all different locations. Okay, so none of them were the correct thing across, or correct same width across basically. And they say, all right, do a Riemann sum using these points here. Okay, so you had to figure out, not only did you have to figure out the upper height for each, but every width was changing as well. But that ceases to be calculus. That's just rectangle 1 plus rectangle 2 plus rectangle 3. Okay?
Which is basically a Riemann sum.
Yeah. But at least the Riemann sum actually has some meaning in calculus. Because remember, if I did the Riemann sum to infinity, I get the definite integral. Okay? And so this is what a definite integral is based on. Okay. Any questions about any of this stuff for the test come Thursday? Okay. So there'll be a video going over all this online. There'll also be in the notes. If you weren't here Saturday, look at the notes and look at the video that's online. If you want to know, okay, and there's another Riemann sum example. Okay, if you must know, I have a YouTube account with a channel.
I follow it.
Okay, that just gives.
Subscribe.
That's just for these classes. Okay, and so.
Nothing else.
It will have the notes. It has videos on it for every class that we've done that's worth taking a video
You
for.
get a bunch of subscribers so you start getting paid.
Do you really?
Yeah.
Yeah.
I didn't know that. Go subscribe, baby.
The ad at the bottom. Kobe Bryant.
I would like to get extra money for buying. No, in all honesty, actually, I wouldn't accept money for its education. I would just do a free license or whatever. But.
Why would you not accept money? It's not like we're paying anything. It's just YouTube. It's YouTube paying you for having ads on there.
Because they get a lot of traffic.
I mean,
Okay,
honestly,
I see the logic there. I guess that is different.
it's not like we're paying you anything. It's
Well,
YouTube.
you are paying me for me teaching.
Right, but we're not paying.
paying you extra.
I see what you're saying. Okay, anyway, if you just do my name in YouTube, I am the first, I should be the absolute first hit in YouTube. Yeah, there are other Stephen Dowells. I think I mentioned this before. There's other Stephen Dowells, but
I don't have as cool.
I like trending videos for this week, and it should be on there. Just sort by like most shoes blindly. Find out.
Darren Shopper.
search myself before. And so, there you go.
Yes.
You see my smiling face, you know you've got the right channel. If you don't see my smiling face, you've got some other random person's channel. Some of them are weird.
Oh, I like this.
Let's go hunt.
I don't know, but
Hi, everybody.
that's what's so shocking about it is
Tell you, Rick.